What is a set associative cache? Well, to explain that, let me first start with the direct mapped cache. So what I'm showing in this picture is a direct mapped cache with the 4 cache lines. And like we said, a direct mapped cache is too restrictive because a given cache block can be mapped to exactly one cache line. And that's a problem because when you have a program that happens to access the cache blocks that get mapped to the same cache line, then you may end up with a poor cache performance. So for example, in this case, if these two are blocks A and B, and if your program accesses A and B alternatively, then you may end up with a cache performance that is very poor. In fact, it's 0 cache hit rate. So we want to create more choice. How do we do that? So let me do the following. So obviously I need more choice. So the way I'm going to do it is I'm going to create what is called as a way. So I'm going to call this as a way 0, what I originally had. And I'm going to take the same cache lines that I had before. Keep in mind that I'm trying to create a different cache organization, but I don't want to increase the cache size. So I had 4 cache lines before. I still have 4 cache lines now, but I have reorganized them. The main change now is that I only have 2 rows as opposed to 4 I had before. So instead of 2 bits, now I need only 1 bit to select my row. So before the row had only 1 cache line, but now it has 2. So therefore, a given address now can be stored in any one of these 2 cache lines that are part of that row. I'm going to call this row as a set. So a set is nothing but a set. A cache set is nothing but a set of cache blocks that are indexed with that share the same index. Okay. Now the color of these need to be changed because the line index for the cache block that is stored in this cache block is going to be same as the cache block that is going to be as the line index of the cache block that is going to be stored in this cache line, right? So what you actually have is 2 sets of cache lines, 2 cache lines that are part of the same cache set. So now I have set 0, set 1. I no longer have set 2 and 3 because we used up those cache lines and added them to the sets 0 and 1. So now if you look at this picture here, it's still the same number of cache blocks like we had before, but they're reorganized in a different way. Now if I have a cache block, let's say A and B, right, they're still mapped to exactly one cache set, but fortunately that cache set has 2 cache lines, which means that now I could store a given cache block in either of those 2 cache lines. So I could store A here or I could store A here, which means at any given time it's possible to store both A and B together in the cache. And that way the pathological example that we had before, where the program happens to access the cache blocks A and B alternatively, would actually enjoy a very high cache hit rate, close to 100% in the steady state. So now I have 2 cache sets, 0 and 1, and we have 2 ways, way 0 and way 1, and that's why it's a 2-way set associative cache. And a given cache block can be stored in any one of the 2 ways, depending on which one is free. How do you know which one is free? Well, this goes back to our discussion on replacement policies and how we handled it in the case of fully associative cache. And so remember that we talked about a policy called LRU, the least recently used policy. So in case of both cache lines are occupied by some cache blocks, and if a new cache block comes around and happens to map to the same cache, the cache set, which is not true in this example, but assume that A, B, and C all map to the same cache set. Now you have to find a victim and evict it. And the way we would find that victim is by using a replacement policy. And if you use LRU policy, then you will check to see if this is the least recently used or if this is least recently used, and depending on which one was least recently used, you would choose that as a victim. So essentially all the ideas we talked about in the case of fully associative cache, the replacement policy, those are applied within the blocks of a set. Of course, across the sets, they don't have any impact. So for example, I may have C and D, and between A, B, C, D, it may be the case that C is the least recently used, but that doesn't matter, because if I have a new block that needs to be stored in the set 0, my choices are just A and B. C and D are not my choices, and therefore it doesn't matter what their LRU rank is. So here's another way to visualize the same cache organization. So this is still a two-way set associative cache with two sets, and because it has only two sets, I have only one bit that I need for accessing, for figuring out which set I should be accessing. And within that set, I have two cache blocks that belong to two different ways, and I have the freedom to store my cache block in any one of those two ways depending on which one is available. Just like in the case of a direct mapped cache, some portion of my address is being used for the set index, and the remaining would be used up by the tag, and the tag is stored along with the data as shown in the picture. So here is yet another way to visualize the set associative cache. So given an address, I would first compute, I as in the cache would compute the set index, and that would depend on how many sets I have in the cache, and we'll talk about that in a moment. So I take the set index and access the particular row, which is essentially the cache set. And unlike in the direct mapped cache where I need to only make one comparison, here I need to make as many comparisons as there are number of ways. So in this example, I have two ways, so I need to compare the given tag to the tags stored in both of the ways. And if any one of them matches, then I can declare a hit. And once I know which tag matched, then I can retrieve the data from the corresponding way, right? So if this tag matched, then I should be getting the data from the corresponding way from the data array. And then I will subselect furthermore the particular byte in that block depending on the block offset, just like what we did in the case of the direct mapped cache. So let's synthesize these three cache organizations into one slide and see if we can make sense out of it. So again, we started off with this idea of a fully associative cache where all the cache blocks were essentially part of the same set, right? So that's one way to think about it, because if I have to bring in a cache block from memory, in the case of a fully associative cache, I can place it anywhere I want. So that means the whole cache is one single set. And that's what is represented here. So if I have a cache with space for 4 cache lines, and they would be organized such that there is exactly one cache set, let me call it as a cache set 0, right? And so another way to think about it is this is just one row. And so if you're going to have only one row, you don't really need a line index. So as a result, your address is interpreted as only two parts. One is the block offset and the other is the tag. And the reason why the set index is absent in this case is because it has 0 bits. Because if I have only one set, I don't need a bit to tell me which set to access. Now for the same cache size, we talked about how to construct a direct mapped cache. In this case, we went to the other extreme and said every cache block is part of its own set. So in this case, we have 4 cache sets effectively, cache sets 0, 1, 2, and 3. And each cache set had exactly one cache block, or rather one cache line, right? And these two are 2 bytes that are part of the same cache block. So I have 4 cache sets, which means that my address will have the block offset, and it should have 2 bits to select my cache set, and the remaining would be my tag. Now, what we talked about just now is a two-way set associative cache where we reorganized it so that each row now had 2 cache lines, or each cache set now had 2 cache lines. So now I have 2 cache sets, cache set 0 and set 1, right? Because total number of cache lines is 4, and I'm organizing them in 2 sets, so therefore each set will have 2 cache lines. So now in order to select the cache set, I don't need 2 bits anymore, a single bit would do. So that's exactly what I would have in this case. Okay, so all of these ideas are consistent with each other, as you can see. I mean, one way to think about a fully associative cache is, oh, I had 4 blocks in the set. So I could even say this is a 4-way set associative cache. I had only 4 cache lines, and therefore I could have only 1 cache set, but that's another way to think about it, right? And if I had a cache of size 8, and if it was a fully associative cache, then there would be 8 cache blocks that are part of the same set. Then if I have to phrase it as a set associative cache, I have to call it as a 8-way set associative cache. That's just another way to think about a fully associative cache. And the trade-off here is, in the case of fully associative cache, I need to make 4 tag comparisons, and that is expensive. In the case of a direct mapped cache, I just need to make 1 tag comparisons. That is much more faster, but the problem is it restricts my choice, and that can result in poor cache hit rate. In the case of 2-way set associative cache, it's somewhat flexible compared to direct mapped cache, but not as flexible as a fully associative cache. And so the cache miss rate can be higher than that of fully associative cache. So the cache miss rate would be the best for the fully associative cache, will be okay for the set associative cache, and probably the worst for the direct mapped cache. So let me go through a few equations which are very useful when you are solving cache problems. It's important that you familiarize yourself with these equations. So we have a cache size which is typically given to you, and you take the block size, and if you divide cache size by the block size, you will know the number of cache blocks that you can store in the cache. Sometimes we refer to the cache blocks as cache lines, but the technical difference really is that cache line, think of it as a hardware physical structure that has space to store the cache block, and along with some metadata such as tag, LRU bits, valid bit, and so on. So a cache line is cache block along with that metadata. But the cache lines, the number of cache lines is going to be exactly same as the number of cache blocks for any problem. And then you have the block offset size. Now this is important when you want to interpret a given address. So if you're given an address of size whatever, let's say 32 bits, the block offset is the last few bits, and the number of bits you would use for the block offset obviously depends on the block size. So if you take the log to the base 2 of block size, you'll be able to figure out how many bits you need for the block offset. In the case of a fully associative cache, everything that remains would be a tag. But in the case of let's say direct mapped cache, the number of sets that we have is going to be dependent on how many lines there are. Now, number of lines is same as the number of cache blocks, which you would have computed using this equation. So the number of cache lines divided by 1. So why is it 1? Because the number of ways is 1 in the case of a direct mapped cache. So we are saying that the number of sets is exactly same as the number of lines, because each set has exactly 1 line, right? And then if you have a two-way set associative cache, you take those cache lines and you partition them into 2 ways, and so the number of sets would be half of the number of lines. And in the case of n-way set associative cache, you are partitioning the given set of cache lines into n ways, and so every set would only have number of lines divided by n. In the case of a fully associative cache, you place all the cache lines into one set, and therefore the number of sets is going to be 1. So n is equal to the number of lines. And now if you have computed the number of sets, then you can figure out the number of bits that you need for the set index as simply log to the base 2 of number of sets, and then you would have figured out your set index, part of your address. And then the remaining part of your address is what you would use as a tag. So the tag size would be the given address size. In our example, it is 32 bits, we said. And then you take away the set index and you take away the block offset. What you are left with is your tag. Now, all this computation of partitioning the address into these 3 parts, it's specific to a cache design. It's nothing to do with the ISA at all, except for this address size specification. So the only thing your ISA defines is the address size. The set index, block offset, etc., they're all specific to the cache design, and therefore they are hidden from the programmer and the compiler and so on, like we talked about a few lectures ago. Now let's use these equations to solve a very simple problem. So you're given a 32-bit ISA, and the cache size is 16 kilobytes, and the cache block size is 64 bytes. And so the number of lines would be the cache size, which is 16 kilobytes divided by 64 bytes. And so when we say kilo in the case of cache problems, we are always talking about 1024, not 1000. And so if you do the math, so kilo is going to be 2 to the power of 10 divided by 2 to the power of 6. So that would be, so we can express this as 2 to the power of 4. And so that's 14 minus 6, that is 2 to the power of 8, which is 256. So the number of cache lines is going to be 256. And then the number of bits that we need in the block offset. So the block offset size is going to be log of 64, which is 6 bits. So now in the case of a fully associative cache, keep in mind that we don't have a set index. And the reason why we don't have a set index is because we have only one set. So you don't need an index to select that set. So as a result, you have only the block offset, which we just computed it to be 6 bits. And then the remaining is going to be the tag. So the total address size is going to be 32 bits because the ISA that we are asked to assume is a 32-bit ISA. So therefore the tag size is going to be 32 bits minus the block offset. So that is 32 minus 6, which is 26. Then we have direct mapped cache, where we have to now figure out what is the size of the set index going to be. So the block offset remains the same, But to compute the set index, we need to compute the number of sets, because we know that the set index size is nothing but log of the number of sets. How many sets do we have? Well, in the case of a direct mapped cache, the number of sets is same as the number of lines, because the number of ways happens to be 1 in the case of a direct mapped cache. So that is 256. So therefore the set index is going to be log to the base 2 of 256, which is going to be 8 bits. So we have 8 bits for the set index, and this is your block offset. And the number of bits for the address does not change across the cache architectures. It's an ISA specification, not a cache specification. So that remains to be 32 bits. So it's 32 minus 8 minus 6, which is 32 minus 14, which would be 18 bits. And so finally we have 4-way set associative cache. So in this case, what's going to change is the number of sets. So the number of sets is going to be now number of lines, and we are going to divide those lines into 4 ways instead of single way like we had for the direct mapped cache. So number of lines is 256 divided by 4, that is 64 sets, which means your set index size is now log to the base 2 of 64, and that is going to be 6 bits. And so the address size again doesn't change. The block offset also doesn't change, because we are asked to assume the same block size for all of these problems. So that remains to be 6 bits. And then we just computed that the set index is 6 bits. And so whatever that remains is going to be the tag. So that is 32 minus 6 minus 6. So that is going to be 20 bits.